All right, didn't get any requests for questions, so I'm going to leave the camera on for about 5 minutes. Again, these are office hours. These are not lectures or lessons. There is nothing prepared for these. So if you got a question, post it in the chat, send me an email, answer it. Otherwise, in about 5 minutes, I'm just going to cut the camera off because I don't think you're particularly that interested in watching me type. And yeah, this is just your time. Problem 5, test for pH from PKA from KA and PKA homework. All right, let me bring up that homework. Alright, so you want to know the pH when you take 124 mLs of 0.956 molar HCN and mix it with 15.4 mLs of 0.00661 molar sodium cyanide. You're given that the pKa here is 9.21. So your reaction is HCN, goes back and forth to H plus and CN minus. I'm not going to bother with the AQs. You should know that at this point. And what we've got here is a dilution problem paired with a pH problem. So we still need our IC table. HCN, H plus, CN minus. H plus, we're going to assume 0, so minus X plus X plus X. And what we need to know are these initial concentrations, because ultimately what we're going to get at is that Ka equals Q, which is H plus times Cn minus all over HCN. So for these two, it's a mutual dilution. They're mixing together. So our total volume here is 124 plus 15.4, which will give us 139.4 mLs. For the molarity of the HCN, we got the total volume is 139.4. Initial molarity is 0.956. And starting volume is 124. We're going to see a similar approach for the cyanide. Oops. Molarity of the cyanide is 139.4 for the total volume because they're together. 0.00661 times 15.4 ml. So let me work that out really quick. 4, 15.4. So for my initial concentration of HCN, I get 0.0850, 0.850. And then for my initial concentration of cyanide, 0.00073. And I'd recommend doing this calculation in Excel. It just makes your life a lot easier. So then I'm just going to plug that in. So H plus is X, cyanide is 0.00073 plus X, HCN is 0.850 minus X. 9.21. So when I stick that into the quadratic equation, I get two roots and the root that makes sense. Is 7.17 times 10 to the negative 7. So I'm looking for concentration of H plus, so if I just take the negative log of X. I get 6.14 or just 6.1. So this problem, only real complication with it, only big difference between it and the previous problems is that you have to work out the starting concentration by looking at the dilution formula. Once you've worked out what the diluted starting concentrations are, because these are being mixed together, which means they mutually dilute, then you just plug into your IC table and you go about like you normally would. Yes, so you're going to assume that the volumes here are just additive. So when these two mix together, you end up getting that 139.4, which is just the sum of the two. It's a weak assumption, but it's the best we have. And for dilute solutions, it's not that bad of an assumption. You're welcome. Any questions out there? So I've been having a lot of issues with it. So to begin with, the lab assignments aren't code I've written. They were written by a coworker of mine. And last semester there was a timer. It required a password. For some odd reason, this semester it's not putting in a password and it's not putting in a timer. It's also not letting you load your work. You just need to email it to me. But ideally, yes, you would be limited to 2 hours and 50 minutes, which is what we do during a normal semester. But for some odd reason, this semester the code just isn't working. I don't have access to this code. It's not my code. It's not. I don't have permissions to edit it. So this close to the end of the semester, I'm not going to worry with it. You don't have a timer. It's not going to require a password, and just email me your work. But the last semester, we definitely had a timer on it. Yeah, if for some odd reason it's just not requiring a password this semester, again, last semester it needed it. Don't know what's going on. Perhaps WebAssign has changed its coding, but it's too late in the semester to worry about it. Correct. So in the previous example, for both the HCN and the NaCN, you need two separate dilution formulas. They both share the same final volume. This is because they're being mixed together, but they have different starting molarities and different starting volumes. But in both cases, you're solving for the final molarity, which is the molarity when they're mixed together. Correct. So you've actually got two initial concentrations. You got the initial concentration before they were mixed, and the initial concentration before they reached equilibrium. And conceptually, that's the hardest parts of these types of problems. Is like you've actually got two steps. You've actually got two problems. You got dilution problems before you even start this, and then you've also got the problem where you actually work out extended reaction and how much they actually reacted with each other. You're welcome. All right, other questions? All right, don't have any concurrent viewers. I'm just going to cut the camera off. Again, I'm here if you got questions, just put them in the chat. So just got a question about solving these pH problems with using the IC table versus using, that was interesting, using the IC table versus using Henderson-Hasselbalch, and why you would pick one over the other. Um, so let's talk about one versus the other. So let's talk about the pros versus the cons. So the pros here is that this always works. So your IC table, if you're given just the acid, you're not given any conjugate base so that A negative isn't there, this can still be used to solve for the actual pH. This requires buffers, and specifically the buffers of, buffers of sufficient concentration. So what do we mean by sufficient concentration? That extended reaction X, generally if it's more than 5% of the concentration of the conjugate base or the weak acid, it's going to start giving you answers that really deviate from what a true IC table work. So this is a true, this should be the most accurate representation of how to solve it. This is an approximation, and it's an approximation that works in what's called the small x approximation. And the small x approximation, we treat it like the concentrations of the acid and the conjugate base don't change that much. So when is that true? Well, if you have high concentrations, greater than 0.1 molar, and your Ka is sufficiently small. But these are all kind of arbitrary statements. So the danger with Henderson-Hasselbalch is that you're kind of having, you should actually go through and prove your assumption. So you should take the pH you get, convert that to H plus, and then divide that H plus by the concentration of the conjugate acid and the parent base, and make sure they're all less than 5%. In most cases, this is going to be true for a buffer solution, but sometimes it's not, particularly if you're sitting on the edge of the buffer regions. And again, Henderson-Hasselbalch is going to work if you're just working with just the acid. Now, the pro of the Henderson-Hasselbalch is that it's easy. And this is why it's used as an approximation, because the other dirty secret here is that this assumes you're working with absolutely pure water. Any tap water is going to have ions in it. It's great that you went through all this work with the IC table, but if you have any type of ions in it, which are generally true with water, you've got iron from the pipes, you've got lead from the pipes, you've got phosphates that are preserved in the pipes, you've got calcium from hard water sources. All of these are going to mess with the pH. So even though this will give you a very precise answer, truth is that you're not working with a clean system that's really that clean. Now, the cons of the IC table, that it's a lot of work. And so you can kind of see how these parallel each other. This is a lot of work, but again, it makes a lot less assumptions. You don't have to go through here and prove, or you shouldn't have to prove that X is sufficiently large. That said, most people use Henderson-Hasselbalch and don't bother to prove it at all. So I would say, generally speaking, Henderson-Hasselbalch will work for any type of buffer. It's a good check. All the homework problems are set up using the IC tables, though. This is because it's the more accurate way to do it. A lot of cases you'll end up getting the same answer, but in some cases you'll actually know you'll notice they begin to deviate. So particularly with that homework 6 problem, where it was like 0.00071 molar sodium cyanide, that's a case where the Henderson-Hasselbalch equation is going to fail because X here actually begins to take on an appreciable amount of that conjugate base. Because what's not really stated in the Henderson-Hasselbalch is we got the pH equals the pKa plus the log of A minus over HIA. It's not written there, but really these are the starting concentrations. These aren't the equilibrium concentrations. We're just going to assume that they're close enough in values that any errors are going to get kind of picked up by the logarithm. And actually, a student emailed me this morning asking about, like, they were doing the homework and they were using the small x approximation and they were still getting it right. And I told them the thing about logarithms is that they compress really large extremes of powers of 10 into very tiny numbers. So if we consider the range 1 to 1,000, that's a lot. But in a log scale, that's 1 to 3. It's 0 to 3. It's not that big a range. So little errors kind of get gobbled up by this logarithm. Again, If you have reason to believe that your approximations hold, particularly with the smallest approximation, Henderson-Hasselbalch's just fine. But if you don't ever want to have to bother with those approximations or making sure they're true, the IC table is the better way to go. And again, we do both. It's not like in this course you can't use Henderson-Hasselbalch and you can't use the IC tables. It's just being cognizant of when Henderson-Hasselbalch's approximations begin to break down. And even then, this actually has a built-in assumption that we don't ever talk about. And the assumption here is that x is greater than 10 to the minus 7. And the reason that assumption is built in there is that water already has a pH of 7. Concentration of H plus is already 10 to the negative 7. So when we build our IC table, we're always stating that the initial concentration is 0. And the reason we're saying it's 0 is that we're saying it doesn't make a meaningful contribution to doesn't make an meaningful contribution to the concentration of H plus. So we always write this out. And we always say this is 0. Well, it's not really 0, it's 10 to the negative 7. But for most of the problems we solve, x ends up being like greater than 10 to the negative 5. So it's 100 times bigger than that 10 to the negative 7. So it's not really that it's 0, it's just that it's so small it doesn't contribute. But particularly, and I think if you work this out for all acids, the concentration of the acid is around 10 to the negative 7 molar. It actually won't dissociate. You will get 0. The Q here for this particular case ends up basically being the pKa. And we never ever work in these teeny tiny hypothetical regions, but they do exist. So even with this IC table, there's an assumption built in that X is sufficiently large relative to water. That definitely doesn't show up in Henderson-Hasselbalch. So I know that's a lot of information to take in. But again, big picture is Henderson-Hasselbalch makes some assumptions. You just need to be aware of them. As long as you stick within the assumptions of Henderson-Hasselbalch, it will give you pretty much the same answer this gives. The IC table will begin to deviate away from Henderson-Hasselbalch on extremes. So if you're not working with a buffer or your concentrations of acid and conjugate base are very small relative to the extent of reaction, that can be happening because their concentration is small. It can happen because the Ka is pretty small or pretty large. This is the more reliable route. But that said, even this begins to fail when the acid concentration gets really, really small. So if you look at the previous problem I worked, to answer your first question, so on homeworks, the pH from Ka and pKa, number 6. So for this one, I get the pH to be 6.14, and I get the starting concentration of the parent acid, the HCN, to be 0.850 molar, and the concentration of the cyanide is 0.00073. So X in this case, the extent of reaction is 7.17 times 10 to the negative 7. If we divide the cyanide, X by the cyanide concentration, it's small, 0.1%, but let's see what happens. So now we have pH equals pKa plus the log of 0.00073 over 0.850. And the pKa for this problem was 9.21. So I actually get the log of this is this ends up giving you 9.21 is the pH. Hold on. Sorry. Actually, that's a typo on my part. 12.27. So this predicts a pH of 12 point. The Henderson-Hasselbalch predicts a pH of 12.3, whereas from the IC table we get 6.14. And so where does this radical difference in the answers come? Well, the issue is here. This ends up being such a teeny tiny number, and the problem with logarithms here is that they're representing power as a 10. So this is 10 to the negative 4. So when I take the logarithm of it, I get negative 4. And we could effectively treat that as just 1. So what's happening here is that this is kind of this assumption that X doesn't make a big contribution here. It kind of does. And because the X is so close to the concentration of the the conjugate base, we end up having to break this assumption that we're close enough or that we can just ignore it. So this would be an example where Henderson-Hasselbalch fails, but if you go to the same homework set, and let me bring it up. And yes, sir, the IC table, so you asked, if you're just given an acid and you're asked to find the concentration of the acid if you don't have any conjugate base, that formula you have there, molarity equals concentration H plus squared over K plus H plus, that's correct. If you work, this is why you work out the IC tables. It'll give you an algebraic relationship for it. All right, pH from pKa. So if we look at the third problem, so the third problem uses HF acid. We have a pKa here of 3.14, and the concentration of HF and the concentration of fluoride equals 0.125 and 0.100. By the IC table, we should get a pH equals 3.0. So if we take Henderson-Hasselbalch, pH equals pKa 3.14 plus the log of 0.1 divided by 0.125. I get a pH of 3.04309, which is going to round down to 3.0. So for the third problem, Henderson-Hasselbalch, the pH here of 3 comes from working with an IC table. And the pH using Henderson-Hasselbalch is roughly the same pH. Now, they're not exactly the same. If you worked out the H plus concentration, this would give a different answer than this. But here, X is roughly 0.001. So if we were to recalculate this and correct it, we'd have log of 1.001 divided by 1.249. So your logarithm there is going to really cancel out those small differences. Now, if you also look at the homework for that one, the pH to pKa, you've got, if you look at the first one, what's the pH of a 0.15 molar solution of hydroiodic acid? So we had the pKa of 1.23, and we've got concentration of HiO3 is 0.150. The reason you can't use Henderson-Hasselbalch in this case, if you look at pH equals pKa plus the log of the conjugate base, which is 0 in this case, divided by 0.150. The log of 0 isn't defined. This ends up approaching infinity. So you'll actually get the pH equals infinity. And for quick answer as to why this fails is that the extent of reaction here divided by the concentration of the conjugate base is infinity. So X is like infinitely larger than their starting concentration. So again, it's just a matter of being judicious with these problems. Like if you have small, like less than 0.1 molar concentrated solutions, or you have incredibly negative pKa's, you're probably going to have to use an IC table. If you have fairly large concentrations, like 0.1 molar or larger, and your pKa is like well above 1 or 2, you can probably work with the Henderson-Hasselbalch equation and get a really good approximation of what the IC table would produce for you. I just don't really recommend, one, the IC tables aren't that hard once you kind of get used to them. And the second is that you always kind of have to go back through and verify your assumptions. And that's my issue with working with Henderson-Hasselbalch. You kind of have to do that due diligence. You can sit back and say, well, it gave me a reasonable answer. It's like, it did, but you need to prove that you're in a reasonable range for that answer to work. As you can see with that pH from pKa and Ka homework, the last problem doesn't seem objectively wrong, but when you work it, it gives you this absurd pH. It tells you it's basic. And it's telling you it's basic because your log is really close to 0, and you're taking the log of something very close to 0, and it just, that logarithm can't handle it. You violated the assumptions of Henderson-Hasselbalch. So for the lab exam, it says that there's a password. It says that there is a time limit. Apparently, that's not happening this semester. Issues with the code. So briefly, what's going to happen is that you're going to be given problems. They look just like the previous labs you've done. You're just having to basically reprocess the data, your open resources. So you can use your lab notebook, you can use your lab manual, you can look at your previous assignments. Big thing is just kind of making sure that you just haven't forgotten how to do those calculations. But yeah, you're going to open it up. You don't have to do any experiments. You're just doing data processing, and they're all based on previous lab. I would say have the web assignments open for reference. And this way, if it does let you see it, you can download your old work and take a look at what you did. No, you're welcome. All right, so we come up to the end of the live stream. Again, if you ever have questions, please feel free to ask them. These live streams are open for anyone, even if you're not taking the course, you just happen to stumble upon the live streams. 5 live streams left. We got the one tomorrow, and then there are 4 next week. Do not forget to sign up for your exam. If you're not able to physically make it to an e-learning testing center, please shoot me an email, and we can set up a way for you to take the exam remotely. Other than that, I will see y'all tomorrow. Thanks for showing up. Do you know if there is any way to make Outlook and Blackboard stop logging me out so often? It's really annoying. No, I think they're adjusting security settings because it used to make me do the authenticator thing like every single time I logged in every day. I think ITS is kind of playing with those settings right now. It's been better for the past 2 days. I haven't had to do the authenticator app, but my guess is that ITS is kind of like trying to find that sweet spot between we need you to log in enough to make sure it's you, but also not so much that it's really obnoxious. All right, see y'all tomorrow.